Continuing on, what is the effect of plastic flow? And in this case, it is applicable to most engineering metals and alloys. That is around the crack tip, um, which is very, very small. There is a process zone, and it is some amount of ductile deformation. And this is the case in most metals and alloys. So if the yield stress is finite, there will be a finite plastic zone around this crack, and there will be yielding inside this zone which will help absorb the energy of that crack and help to mitigate the or stop the crack from proceeding further. But if you don't have that, if the process zone is pretty small, that means there is nothing to stop the crack. So we will adapt this to the case of composites. Okay, so in this case, we will talk about the size of the plastic zone, and this is based on the solution for sigma 22 for mode 1 loading in front of the crack. So when theta is equal to 0, the value inside the square bracket will become equal to 1. So, which means that you can say that the plastic zone size can be derived to be equal to a function of the square of the stress intensity factor divided by the yield strength. So that means that if the yield strength increases or it becomes more and more brittle, the plastic zone size goes down. So schematically we can say that if the yield strength goes down, the plastic zone size goes up. So they have an inverse relationship. Trying to derive this in this class is going to be a little difficult. So basically, what you need to understand for fracture criterion, there are two zones around any given crack. So there is a plastic zone and there is a K zone. In the K zone, the stresses are determined by the stress intensity factor, and in the plastic zone, the stresses are determined by the yield stress. So if your yield stress is pretty high, that means your plastic zone is going to be very, very small. That means the way this material is going to fracture is only going to be controlled entirely by the K zone. So you have two zones, one is the K zone and the other one is the plastic zone. So if you assume that the K zone is pretty large and all the stresses are governed by the K factor, so the crack will advance only when the bonds can break. So if you have a brittle material which has got a very, very high yield stress, whatever governs this has to be driven by the forces acting on the boundary. So in any case, what you will have, the case you have is that you will have you have to have the stress intensity factor exceeding a critical stress intensity factor, and if it is in mode 1, then you call it has to exceed the stress intensity factor K1C. And in brittle materials, you have to understand that this plastic zone is small compared to the K zone, and want to emphasize that K1C is a material property. So what is the material is going to control the property of the stress intensity factor. And so how the material is going to behave in presence of an applied stress is going to be determined by the critical stress intensity factor of that material. So I have posted this, and I think I asked you about this Roy Rice papers on ceramic toughening theories. So please take a look at that. These came somewhere around the mid 80s, and also there was one paper, a follow-on paper that appeared in 1988. These are, I mean, there has not been much change in the behavior of these materials or how they have been analyzed, and so these theories still hold very much, they still hold good. Okay. So, and the other thing I wanted to ask you is to take a look at the paper by Anthony Evans that has also been posted on D2L. And this is your homework 3. I would like you to take a look at the phenomenon of ceramic toughening due to the presence of weak interfaces. So why I mean, it may sound a little bit mixed and jumbled up, but what I want you to understand is that the critical stress intensity factor is going to control how a brittle material is going to fail. Okay, so the whole point of adding all these additives and fibers and second phase particles, etc., is just to improve the critical stress intensity factor. And that critical stress intensity factor can be increased by the presence of fibers, because you have to expend that much more energy in order for that crack to pass through. So now I stop right here, and we will we will go to the next set of slides.